Alright, so after all of that prep work and background, we wanted to go through that whole thing about the inverse sine function because now we can use implicit differentiation to find the derivative of the inverse sine function or the arcsine function. So again, keep in mind that if y is the inverse sine function of x, then that also means that x is equal to the sine of y. And that's the fact that I'm going to use to figure out this derivative. I'm going to use implicit differentiation on the right-hand piece there. I'm going to find the derivative with respect to x of both sides of the equal sign. So the derivative of x with respect to x, of course, is 1. The derivative of the sine of y with respect to x is the cosine of y times the derivative of y with respect to x. Again, that's really using the chain rule, saying that y is a function of x, but maybe not an explicit one. So if I solve that for dy dx, I'm dividing both sides by cosine y. I have 1 over the cosine of y. Now the question is, can I write that just in terms of x? That's what I'd like to be able to do. All right, so can we write cosine y in terms of x? And of course, the answer is that we can. The question is, how do we do it? So we're going to hearken back to our right triangle trig. We're going to make a little right triangle here. And we have that x equals the sine of y. So I'm going to create an angle y in my right triangle. And I'm going to remember my SOHCAHTOA. That is, for a right triangle, the sine of the angle is the opposite leg over the hypotenuse. And since I already know that the sine of y is equal to x, that's where I started, then the sine of y equals opposite x over hypotenuse 1. And now, if I know two sides, well, one leg and the hypotenuse of my right triangle, I can find the other leg, that is, let me just call it L, leg squared plus leg squared equals hypotenuse squared, or leg squared equals 1 minus x squared, or leg is plus or minus the square root of 1 minus x squared. And in this case, because I'm talking about lengths of triangle sides, I'm going to use the positive square root. So this other leg must be the square root of 1 minus x squared. So then, using CA from SOHCAHTOA, the cosine of y is the adjacent leg over the hypotenuse. That adjacent leg to angle y is the square root of 1 minus x squared. Again, technically over 1, but dividing by 1 doesn't change that. Now, just so you know, another way that you could approach this is using the Pythagorean identity, sine squared y plus cos squared y equals 1. Again, I'm trying to find cosine of y. Cos squared y then is 1 minus sine squared y. The cosine of y, taking the square root of both sides, is plus or minus the square root of 1 minus sine squared y. Right, but I can substitute for that, because the sine of y is x, that the cosine of y, and again I'm eliminating the negative square root because it's not a valid solution here in this case. Substituting for sine squared of y, again, from the very beginning, the sine of y is equal to x, so I can substitute x for sine of y, and the square there, sine squared y, means I have to take the sine of y and square it. So I could come at it from that angle too. Either way, I have that the derivative with respect to x of the inverse sine of x, let me just write that a little more neatly, is 1 over the square root of 1 minus x squared. Now, I'm not going to go through the derivation, but I might ask you to on a quiz or a test, so maybe you'd like to go through them for yourself. The derivative of the inverse cosine of x is negative 1 over the square root of 1 minus x squared. And the derivative of the inverse tan of x is 1 over 1 plus x squared with no square root on it. So FYI, these are sprinkled throughout section 3.6, and these again are some more rules that you have to know. And it says right underneath here, be sure that you can reproduce the derivation above and that you can use a similar process to derive the formulas for the derivative of inverse cos x and inverse tan x. So I would make sure that you go through each one of those for yourself. The process is similar to what I just did for the inverse sine of x, and just make sure that you can derive those.